Kia ora koutou. My name is Dr. Joshua Emmitt, and on behalf of my colleagues, today I'm going to present on volumetric reconstruction of archaeological deposits using point cloud data. And this research is really the culmination of a few years of trial and error and research out on Ahuahu Great Mercury Island, where we've used a range of 3D technologies and have really started to carefully consider why we're using different technologies and what benefits some have over others. In archaeology, 3D data is increasingly utilized. I think you'd be hard pressed to find an archaeologist these days that isn't encountering it in some form, whether it be in the form of total station data or 3D recording of excavations, or even LiDAR accounts, object recording in the case of museums. And it's really opening up new methods of analysis. So we're able to consider formational processes that previously were a bit elusive. We're able to map modeling, we're able to model the way that objects are made and how they're constructed, and a whole heap of other questions like volumetric analysis that we really haven't easily been able to do before. And in the case of fieldwork, there are numerous different methods that are available for use. But at least in terms of trench recording, they all have a common goal, which is to record the excavation at a particular point in time. In the past, the methods have been relatively slow and cumbersome, and they've caused quite a delay to the excavation. The area had to be cleared and cleaned quite extensively and then left for even up to an hour. But that's now changing, and these processes, while being a lot more efficient, are also more able to fit seamlessly into our current recording standards. So the question is then, which is the best way to record an excavation? And another question would be, how is the way to do it? And today I'm going to compare three methods of excavation recording, the data from which are used to create volumes of the excavated deposits. So the methods in question are photogrammetry, LiDAR using the Simultaneous Localization or Mapping algorithm called SLAM, very catchy title, and total station recording. So just briefly why we're looking at Ahuahu in this particular area. So on Ahuahu, the area of Waitetoke is of particular interest because for understanding horticultural development on the island. It's in a swale between dunes and a hill slope at the southern end of the Tombola. And we've investigated over several seasons because we found early evidence of taro production there. And in the area, a system of channels with small check dams or weirs have been excavated, as well as cultigen raised beds, which were all used in taro production. This study used one of the excavations, CAAA2021, to test the different methods of 3D data acquisition. So CAAA2021 is a 1 by 2 meter trench that was excavated by stratigraphic layer, with every object over 20 millimeters encountered recorded with a total station. Another 25 centimeters was excavated around the edge after it was deturfed to provide a stable edge. And this was done to stop grass and loose soil from falling back in, but also to create more of a stable environment for model alignment. When a new deposit was reached while excavating, the surface was cleaned and recorded with photogrammetry, total station, and the GeoSLAM, which is the LiDAR scanner that uses the SLAM algorithm. The photogrammetry was collected with a Canon camera. Targets were placed around the excavation, which you can see there as white, along with two poles at either end of the excavation with more targets on it. And this was done to align the many models that consisted the trench, and also they were done to redundancy. So not all of the targets were used in every model, but there was enough that we could align them all with what was captured. So the SLAM, as I said, was done with the GeoSLAM Zeb Horizon. The 4 bases were positioned at the corners of the trench, and when every deposit was recorded, it was the 4 corners and then 1 in the middle of the trench. And we found that extra point in the middle of the trench, or the base in the middle of the trench, was needed to really capture the walls to a point where they could be reconstructed. And finally, total station services were recorded with the Trimble S7 robotic total station. The corners and sides of each surface were recorded, enough to capture the topography, and then about a 25 centimeter grid across the interior of the trench was captured. To actually process the models, a range of different software were used. Photogrammetry was processed with the stock standard Agisoft Metashape. which is a pretty common photogrammetry tool. And it does the job really well. And it's relatively easy to export models from there into a GIS platform. Total station volumes were created in Blender. So the shapefile data was processed in this case, Esri ArcGIS, but any GIS software could do it. And then the shapefiles were imported into Blender using the Blender GIS add-on. They were triangulated and then merged together to create a volume. And the SLAM data was processed in the GeoSLAM software for initial processing. And then it was put into the open source cloud compare to try and create a stable surface from the SLAM data, which it wasn't quite able to do. So we used the proprietary GeoMagick software, GeoMagick Wrap, which did the job by averaging the points. Effectively, there wasn't enough stable architectural features in the area, which is a natural area around the trench, to create a solid surface for the trench. We got one that we could work with by averaging it, but it was a pretty aggressive filtering tool. So probably not the most ideal method for this case, but if you had a lot of built features around, or maybe parked some cars around the trench, that could work. But I'll talk more about that later. So effectively, with the surface data from total station, the top and bottom was captured, and then just a straight linear relationship between the two surfaces established to make the volume of a deposit. In the case of the SLAM and the photogrammetry data, the models of two deposits that were superimposed were aligned, and then the extraneous area of the bulk above that layer, if there was any, was cropped out before they were merged and then brought into Blender to basically use an octree filter to remesh the entire trench into a coherent volume. And that was octree level 8 for anyone that was interested. So in addition to the triangulation and the octree reconstructions, we also attempted a convex hull reconstruction of the trench. So a convex hull just creates the minimum convex area around a set of points. It's a relatively quick algorithm to implement. It's available in a lot of other open source software as well. And I think ArcGIS can even create them like that. So we wanted to test what that would be and what difference that would make to creating volumes. And so you can see here on the screen the two comparisons between our mesh on the left, which is the triangulated mesh, and then the convex hull method. And at the bottom, you'll notice on the convex hull, you'll see one called artifact points. And these were basically just the points of all the objects that were found within a deposit, which had a convex hull around them. And we really just wanted to see if that would provide a indicative volume of a deposit as an alternative. And the volumes and surface areas of all of these, once we've done this, were created, calculated in Mesh Lab, the open source software Mesh Lab for consistency. So this is a visual comparison between the photogrammetry and the SLAM models. So what you're seeing on screen is the photogrammetry model with the difference to the SLAM presented as color. Basically, green is where you've got more of an agreement, and red and blue are basically a disagreement between the two models, away or overlap or away from it. And basically, you can see that the main discrepancies are coming at the corners and the edges. And with the SLAM data, considering it was more difficult to establish a surface on the edges, that's not particularly surprising. The corners, most modeling software, especially photogrammetry and SLAM, they have trouble with corners, particularly with the type of data that we're looking at, because we're thinking about a trench, it's not a hard corner like a perfect cube. It's a little bit rounded and got trench marks and rocks and things. So that's where we're getting most of the discrepancy. And we've mapped all of those using Cloud Compare just to try and get a handle on where our most variation is occurring. And that's that image on the right there. We also did this for the photogrammetry to the total station volumes. So you can see that on screen is the total photogrammetry model with the total station difference presented as color. And this one, again, the edges are where you get the variation, and that's not surprising considering the total station is a straight line, so a straight wall. So what you're seeing as color is really the variation in the photogrammetry, where it's got bathtubing or undercutting of the trench. I know excavators like to think they get their walls perfectly straight, but I've got the hard evidence that they don't. What is interesting though, it's a little bit, might be a little bit hard to see. If you look at the right-hand image at deposit 1 up the top there, at the northwest view, you can you see how on the surface there's little blotches of red. And that means there's a discrepancy where they weren't recorded on the total station model. And that's because that's grass. That's what you can see. So the total station, because it's taking less points, it's creating a much more abstract volume as opposed to, say, the grass, which is captured by the photogrammetry and SLAM data. So we are getting a little bit different. It is a different resolution between the two methods. And that needs to be taken into consideration as to maybe what's the best method to use. That color combination wasn't quite enough to really establish what the best way to go about this is. So we did a statistical comparison of the volumes and surface areas. And what we found, interestingly, is that there was no statistical difference between the volumes that were calculated for the total station photogrammetry and SLAM triangulated mesh models. They're all much of a muchness. But there was a statistical difference between the triangulated meshes and the convex hulls, and between the convex hulls themselves. And so basically what it's saying is that with photogrammetry, total station, and SLAM, you're going to get about the same result, but with convex hulls, you're going to get much more variation. And the question is why? So with convex hulls, what you're getting is effectively an idealized mesh all the way around, and it ignores concavities. So if you have something like a drain feature, where it dips down at the bottom of a trench, you're going to get a nice smooth bathtub across the whole bottom of your trench. It's not really going to account for where the surface of a trench goes back in a concavity. So you're going to get an overrepresentation of the volume. And that image on the left there, comparing the convex hulls to the triangulated meshes, triangular meshes in black, and the gray is convex hulls. Convex hulls are really overrepresenting the volumes in every case. And the point meshing really doesn't reflect what we're getting from the deposit itself. So that's not a great proxy for establishing a volume. The points would, however, calculate a good volume if your point distribution of artifacts roughly match your deposit, because then they're going to be spread out enough to do that. But this wasn't the case without data. Because there was no statistical difference between the photogrammetry, total station, SLAM data for the triangulated meshes, we wanted to have a look at see was there any variation at all. And the way to do that would be the rank order, which you can see on the right there. And effectively, most of the time, photogrammetry is giving you the largest volume, SLAM's giving you in the middle, and total station's giving you the least volume. And that I am interpreting that as basically because photogrammetry is accounting for more variation within the surface, concavities, and convexities. It's just accounting for more variation, and so you get a higher volume. SLAM is roughly similar, but as I said, there were difficulties in calculating their volumes. That's probably where that's coming in. And then total station is more of your clean, idealized exterior of the trench, what that maximum excavation area is. But this isn't a statistical difference. We're really zooming in on the data to see this. So yeah, there are much of a muchness. So what did we learn from this experiment? Well, the first thing is you probably don't need to do both photogrammetry and SLAM. The volumetric results are effectively the same. Photogrammetry does have the bonus of a color texture that's automatically applied to the model. It's when you look at SLAM and LiDAR reconstructions, they're not usually capturing color as part of their capture. It's kind of doing a superimposition at the same after the fact, whereas color is part of the photogrammetry reconstruction. And so if you want that kind of aesthetic angle, then photogrammetry is probably the way to go. It's also, in terms of technology, probably the cheapest. You just need a camera. You can do it with a smartphone, although we would highly recommend that you use a tripod. You might think you've got a steady hand, but photogrammetry doesn't hold any bars. However, with a different LiDAR method, with new generation technology, with new cameras that are coming out, maybe that will change in a few years. I know that you can get LiDARs on smartphones now, but so maybe that's going to change. The total station volumes are comparable and they require less post-processing than the photogrammetry or the SLAM. You can just need an open source GIS software and open source Blender to do it, as opposed to say Agisoft or whatever LiDAR system you need. The convex hull's probably not worth it. We don't think that they're going to give you a good result. Probably a bit too much variation, too much hanging off whether they're going to really reflect the volume of it or not. So what would we suggest? We would say that if you want to do 3D volumetric reconstruction, and you can, photogrammetry at the end of excavation gives you a nice aesthetic result like you see on the right. You can pop that into your GIS and overlay deposits and points. For volumetric reconstruction and representation of your deposits, total station or the like, even GPS is probably the way to go. The recording doesn't take too long if you've got a relatively small area. Of course, that's another factor. And so you can put those on top of the photogrammetry and GIS and superimpose them. They're going to give you an indicative area of your deposits, and then you're going to have the photogrammetry on top, and that creates a nice model. So we've implemented a lot of different technologies on Great Mercury, and we've tested these, and that's probably really going back and reflecting on it. That's probably the most efficient workflow that we've been able to work out. Having said all this is 2021. Next year might be different, and we can only hope that it's going to become more efficient in the future. So thank you very much for your time and listening to the talk. And please, if there's any questions, get in touch. Thank you.